All right, good afternoon, everyone. We're going to now have a panel discussion with all of our participants, or our speakers from this morning. We'll continue to answer the Slido questions that have been coming up since earlier today, and kind of go from there, since it looks like we have plenty to go through. So if all the panelists can turn their video on, so we can see them. Thank you. And I'm trying to get okay, here we go. All right, the Slido up. So I'll read out the question. Whoever wants to kind of take it, jump in. So our first question is, when people say they constrain models by physical laws, mass, continuity, energy balance, etc., using neural networks and GCMs, is this done in their cost function?
I'll go ahead and answer since no one else is jumping in, unless Karthik wants to.
Sure, I can say a few things, and David, you can join in if you have other things to add. David actually mentioned this towards the end of his talk about an hour ago. You can incorporate these laws in the loss function as penalty terms. Besides your standard deep learning losses, you can add extra terms, which could be, for example, the residual of the energy equation or the mass equation. That's one way to do it. But you could also do it in the neural network itself. For example, the last layer, again, as David mentioned, a sort of PD constrained layer where you essentially satisfy the mass continuity equation or energy equation. And again, David mentioned this as well, which is to get results that are projected onto the manifold that satisfies these laws. So there's at least 3 different ways of doing it. I imagine that there will be new clever ways of doing it in the future. This is a very active area of research. There's papers coming out in not just the earth sciences, but also in applied math and other physical sciences, fluid dynamics, dynamical systems, and so on. So there's a few different approaches to doing that.
Our next question on here. What sort of scenario would make a leaky ReLU more appropriate than a ReLU activation?
I do not know, so I'm not going to try to answer that one.
Yeah, based off of my experience, the leaky ReLU is helpful if you're having trouble back propagating information through your network. There are instances where using a regular ReLU, because it sets everything to 0, sometimes you can get a lot of we call dead neurons, where they're basically just all the weights become 0 and they never activate or do anything. So if your model isn't performing very well, switching out ReLU with leaky ReLU can be helpful in those situations.
Yeah, I've seen in a lot of models, like UNet shaped models where you have an encoder and a decoder. On one branch, I think on the encoder, there were a bunch of leaky ReLUs. On the decoder, they were just normal ReLUs. But I'm not sure why. Those are just patterns I've seen, but I didn't really understand them. I think your explanation probably makes pretty good sense.
Yeah, and kind of the GAN type setups, sometimes leaky ReLU seems to work a little bit better. But a lot of it's kind of empirical testing. Try one versus the other, and you like activation functions are one of the more sensitive things. So you might be able to get a decent improvement by switching.
Also, I imagine that with I don't know the exact chronological order of when ResNet came out and how popular leaky ReLU was then, but ResNet essentially was a sort of solution to the vanishing gradients problem, which David mentioned. So perhaps around that time, ResNets became more useful, use leaky ReLU.
Right, let's see. Our next question is, how does deep learning apply to gridded data that have interactions with each other?
Go ahead, Karthik.
I'm trying to understand what exactly you mean by interactions. Do you mean correlations in space and time, or do you mean different variables that are all associated through the physics of the system? I'll maybe try both, and we'll see if there's a more refined question that comes up. But for spatial and temporal correlations, as we mentioned, you can do 3D convolution. So for example, if you have 2D in space, 1D in time, you can incorporate essentially features and correlations that exist in the data both spatially and temporally. You could also do this coupled CNN LSTM or CNN RNN, CNN transformer types of solutions that account for temporal correlations and spatial correlations and are coupled together. If you have multi-dimensional data, so multiple different variables, let's say you take a GCM and you have say 20 different physical variables coming out of it, and to begin with, you don't necessarily know which ones are more useful than the others. A sort of vanilla approach might be just start with all the variables and put them all into your CNN. And then you can apply interpretability tools to figure out which variables are more important than others. So your network itself might tell you which are the most important variables, and you would use those, and the interactions between those will be accounted for. There might be other senses of the word interactions. I don't know if
yes,
David
there's I think Karthik nailed it, but there's also some other options like fully convolutional networks. There's also this conv-LSTM, which when I look at them, they were very expensive to run, but it's an option. Yeah, so there are some options.
One other related idea to that question is that if you think of a big array of images, pixels in an image, and you stretch them all out into a line, you've lost the relationship of what's next to what. So you would think that that's maybe not a legit thing to do because this guy's next to that and that guy's next to that. But what's really happening is in an image, this pixel, which is next to its neighbor, means that those two often have the same value because there's lots of areas that have like a single color, or that could be an edge. So there are certain patterns that show up in the data that are meaningful and many patterns that aren't. So if you pick a random image by assigning values randomly, it just looks like noise. So you can think that the vast set of images in this large space are just basically noise, and that the images that are interesting and meaningful and have interactions between neighboring pixels are a very, very low dimensional set in this very high dimensional. So it's a little low dimensional manifold, and that's what you're looking for with your function. You're trying to fit a curve to the stuff that's meaningful in this giant space of noise. So in that sense, there's interactions between pixels, whether they're images or simulations or whatever as well.
The next question is, are hidden layers doing the same tasks as Fourier transforms?
I'm not sure what they're doing. Like, there's some ways of interpreting them.
My first answer would be no, they're not. Fourier transforms are extremely well understood, been used for centuries now. We have very clear ways of interpreting what Fourier transforms do. Hidden layers are a lot more nebulous than Fourier transforms. That said, there are methods that are actively being developed on essentially doing a Fourier transform to your data and then using a neural network on that. So on the Fourier transform data, this has been done for speech, for audio, but people are also doing it for physical systems because we know that in physics, a lot of these fields, velocity fields, pressure fields, etc., are composed of basis functions that are related in some ways to waves, and Fourier transforms would be sensible. But no, Fourier transforms are different from what hidden layers are doing.
So a slightly different answer that was from my slide on single layer neural networks. They're not strictly the same thing, but you can kind of think of of each of the little ReLUs as a little activation function is sort of like a basis function, right? Because you add them together to construct another function. That's what basis functions do. And Fourier expansions are a very specific set of basis functions, sine waves basically, that can cover whatever function you want. So they're similar in the fact that they're both basically basis functions you can construct more complicated things from. As you go into higher and higher levels in a deep network, these features become more and more abstract. So they become less and less like traditional basis functions and more like something you would call a feature, like an actual face or a cat or a hand or something like that. So you can kind of still think of it like a basis function you can use to construct these bigger functions, but it becomes more abstract. I don't know if that's a good answer.
That sounds good. I think we'll go ahead and move on to the next question. How do we differentiate between poor data quality, example, poor images trained to CNN or some other kind of data issue versus the model is just overfitting to the data?
I mean, the first thing you can try is to just look at the difference between training and test set or a validation set. You know, just look at how different those performance are, and that tells you whether the model is overfitted. On a different level, you could actually ask your network to predict the error, and you can supervise that implicitly using the loss function, and it can tell you what it thinks the data quality is. So you compare that with the total error, you get a sense of how much of that is due to data noise, how much is due to in overfitting.
So I agree. The main way to tell if you're overfitting is just to see if your function generalizes. Overfitting means it's essentially memorized the data you gave it and has no idea what to do when you give it new data. So when you when you test it out on your test data or your validation data and it gives you the wrong answer, and even though your training data looked great, so those numbers are very different, that means you overfit. If you do a really good job and like your training and validation curves are exactly the same and your model has the right capacity and everything's looking good, but your answer still isn't accurate and kind of terrible, it probably means your data is not any good or you don't have enough data or it's biased or something. So yeah, you can tell overfitting just by comparing training versus validation most of the time. Other problems are harder to diagnose.
Our next question is a sort of LSTM question. Which approaches do you recommend in time series forecasting for LSTMs? Do we do a one step ahead prediction, retrain with a new observation, then one step predict again? I'm assuming this is in opposition to just like letting the LSTM run forward with additional predictions, or like where you give it predicts and then it uses that prediction to predict the next step.
Yeah. Suppose this is a follow-up on the DI that we talked about earlier. And in the DI, we essentially set the lagged observation, use the lagged observation when it's available to replace the model's own prediction. And we don't have to retrain it in the sense that we only train it once. So it's figured out whenever there's a valid observation coming in, how to utilize it. But yeah, you don't have to iteratively retrain it. That would be kind of cumbersome. I don't know if that answered your question. So basically in the input you have all this forcing data, you have all the attribute data, but you also have the you also actually sorry for this if you have missing data in your Y target, so you have an output which predicts at Y, then you have another loop that kicks in and replaces the value if you have a valid observation. That's how we handled it. There's no need to retrain it.
Okay, our next question is, most of the interpretability tools are done in the context of classification. Do you have insights regarding interpretability in regression contexts? I should say we'll hear more about this on Thursday, and they'll talk about both regression and classification approaches.
Yeah, I'll just add to that is, you can think of regression as essentially many discretized classification terms. So you can essentially discretize your regression question into classification over many points. So in principle, you can extend your classification interpretability tools to regression questions as well. But of course, we'll hear more through the week.
Yeah, so I saw a talk by, I believe it was Elizabeth Barnes, who did a reverse layer-wise propagation to determine what things were determining what in her neural network, and that was a regression. So she was showing climate states and having it mapped to the year, and then she checked for a given year what were the features in the climate that it was using to identify the year without it knowing what the year was. So reverse layer-wise propagation in that case was a regression where you could, and it showed certain features of the ocean, changing temperature, and over land, certain patterns that were unique to that year, helping the network to determine what year it was. So that's an example.
And our next question, we've kind of addressed this a little bit already, but I think there's a slight tweak on this one. Is it possible to incorporate the knowledge gained by deep learning models into current NWP models and how to deal with the parts not consistent with physics?
I can take a stab. It's not trivial or easy to do that. One example you can think of is using deep learning models to, let's say, build parameterizations. In some ways, the deep learning model is learning some new dynamics and physics about these processes that are parameterized, and then you try to couple that into your NWP models. There are likely parts of the outputs that are not consistent with the physics, but then hopefully the fact that you're coupling it with a numerical PDE solver means that the PDE solver will take the heavy lifting of essentially correcting some of those unphysical parts. But then, of course, the challenge is that you can have instabilities. So if you end up having a deep model that produces results that are extremely inconsistent or have perturbations or other types of instabilities that can totally throw off the coupled model. So there isn't quite a straightforward answer to this, but
yeah. So
there's
I agree with Karthik. I mean, so there are a lot of ways you can use deep learning in numerical weather prediction models. And the way he mentioned, basically taking a physical parameterization and then replacing it with a deep neural network that's supposed to do the exact same thing, but is a heck of a lot faster, is the most popular thing you can do. But yeah, you have to be very careful, because if it produces that output that's non-physical, doesn't conserve energy, your whole model can be thrown off and become unstable. So people are still working on getting that right. A team from MIT showed a physical parameterization that is stable and does a very good job of this. There are other things you can do. You can use high resolution simulations to make a better physical parameterization and replace the ones you have. You can also do direct prediction of numerical weather prediction for like nowcasting for like the next couple hours. There's like a paper from Google on that, where they showed that they were able to beat actual physical models for about an 8-hour window, after which it couldn't beat them anymore, but that is lightning fast. So there's a lot of different ways to apply this to NWP. But yeah, maintaining physical accuracy is a challenge people are working on.
And not only for NWP, but in the field of hydrology and related some other domains, I've seen a lot of work on physically informed neural networks where you use data to constrain the models, and you essentially get your new governing equations. So in a sense, of course, you can update your model with the new equations. right? So that's a way of fixing dynamics that you didn't know before.
Another question. I bumped it up from below, but I thought it would be kind of interesting to discuss with this group. Other than being computationally too expensive, what are the other challenges of auto ML?
Although I presented AutoML in my talk, I'm not an expert on this subject. It's something that the cloud computing guys love, because if you can get AutoML working, basically you don't need all these deep learning scientists anymore and with 10 years of experience. You just need data, and then the computer does everything for you. I mean, it's a nice idea, but there's a long way to go before we get there. The closest thing they've got is neural architecture search, where you can actually see the idea of searching through all the possible architectures within some space and finding ones that work really well. And there's been some good progress there. But all the other steps, you know, determining all the things that a data scientist has to do that you guys are trying to do in the hackathon from end to end without any human input, it's pretty challenging. So I don't know. I don't know specifically what I would call the biggest challenges, but it's a really hard problem.
Does anyone else want to comment on that one?
I have not used ML before. It'd be fantastic to try. What would be actually mine would be a question, like what would be the simplest software tool to try in this young?
I might add one point, which is that you still need to specify what types of hyperparameters you want the AutoML to optimize on. So in some ways, there's still work to be done from the scientist's point of view in designing what type of model and what type of, you know, what are the characteristics of that, which of those free parameters or hyperparameters you'd like to optimize using this sort of method. So it's not that, you know, everything is solved using AutoML. There's definitely a lot of sort of design of experiments work that needs to be done before that.
All right, next question. Following up on NWP using deep learning, each time the model physics is upgraded or modified, will this require rerunning any ML or deep learning training, presumably?
That's a good question. David mentioned transfer learning. This is a classic example where you could attempt transfer learning. So you have a trained model that's run on the last version of your NWP model, and then there's some new changes and a new version comes out. You could simply just apply that pre-trained model on the new version, and it's likely going to work well. And if it doesn't, then you might only need to augment with a little bit of extra training data and perhaps retune some of your parameters with that extra data. So you don't need to start from scratch. So this would be a classic example where you could use transfer learning.
Yeah, I agree.
Another question I just bumped up. Can you use Gans to artificially increase your training data set?
That's a sort of yes and no question, right? Yes, people do that. You can, if you have just a few examples and you want to generate more, you can teach again to try and learn that distribution and create new examples. Like, you can kind of think of it as a augmentation technique where you're taking the same image and just tilting it around and flipping it. It's another way to augment your data. But you're not, if you don't have enough points to really flesh out your distribution, you won't get great generalization, right? So you can get a little bit with that, but you can't go too far because you just don't have enough information. So yeah, it helps, but it's not, it doesn't solve, it's not like a magic data fountain or something.
So next question, how do I make the choice of using a common CNN architecture such as VGG or AlexNet versus building my own model, especially when working with, say, satellite imagery?
I'm waiting to see if Karthik's going to jump in.
Sure, I can start, and I think David might have more to add. I'd say start with an existing architecture. You'll be surprised how well some of these pre-trained networks on totally different problems might work on your data set. Some of the features that these networks are looking for, edges and curves and these compositions exist in all types of data. That said, you will have to continue optimizing the model in order to perform well on the specific task that you care about. So it's not simply just applying it as is for the final goal, but it's a good starting point.
Yeah, I agree with all that. Sometimes your input, like from satellites, might have 16 channels, and the normal VGG network was pre-trained or only anticipates 3 channels, and then maybe the data is not so easy to get into that format. So you might have to add a little bit of a network to the beginning to transform it into the right format, or you can use VGG and things like that as basically a feature extractor for a totally separate network that you then train on your data. There's a lot of different ways to do this. Choosing the right model, it doesn't take a lot of work to take a pre-trained model off the internet and apply it to your data if it fits the format. So I would just try them. Trial and error is a pretty big thing in deep learning.
Another question I pulled from further down the stack, but I think is kind of relevant. How do you aggregate the error function for an image? Do you do a grid cell by grid cell and an average for every grid cell? Do you weigh each grid cell differently? What has worked for the panel?
Well, I could start, and then I'm sure there's many different answers. I wouldn't necessarily average because you could cancel out positive and negative errors. So that may not be the best idea. Part of what these pooling layers do is to essentially reduce the size. So hopefully you're not computing the error over all of the data, all of the individual points. You could also add error functions for things besides just the specific pixel loss. So for example, as we mentioned earlier, you could have physics-based losses. You could have other losses corresponding to geometry and topology and so on. So you're not necessarily just relying heavily on the pixel loss. I don't know if David or Chaopeng have other things.
Yeah, so the loss function is basically what you're talking about here. The error function is the loss function. And that's a hyperparameter. It's something you choose. It basically indicates what you think makes a good answer. So if you have this image and that image, how do we compare them to make sure they're similar? And there are a lot of different loss functions you can use. Like the L2 loss function basically does a pixel-wise difference, squares them, adds them all together. So it's the squared error. You have the L1 loss function. And then a GAN, like the whole second part of the GAN that tells you whether it's a good image, a real image, or a fake image, and passes that information back. That whole classifier part can be thought of as a custom loss function. And then if you're comparing distributions, you might use something like the Wasserstein loss, where it has a bunch of points compared to a bunch of other points. So instead of image to image, it's like a set to set comparison. It's a big area of hyperparameters. There's a lot of different ways you can use your loss function. It requires some knowledge of your problem, I guess.
I'm going to do one more question, and then we'll wrap up the panel. And I'm going to, since there's a couple there along the similar theme, I'm going to kind of try to bridge them together. This is, how do we use a trained machine learning model trained under current climate to predict, say, future hydrology or any kind of future climate or extremes, say in 2050? What happens to the weights, and is there anything else we need to change in the model? What do we know, and what don't we know about this?
I want to hear what Karthik has.
It's actually a good question. Very good question. A very
It looks like Chaopeng, you
things
froze up for a second.
Okay. So a very ordinary way, you just take the climate forcings from the climate model and pass it into, let's say, our hydrologic model to simulate stream flow or soil moisture. And then you can, analyze the outputs from there. But I think the more difficult question with the climate models are like how much fidelity do you have in those climate models, and how much skill do you have in those climate models, and can climate models actually reproduce some of the essential dynamics or weather events. For example, extreme events, can they reproduce the frequency and magnitudes of these extreme events? According to my limited knowledge, I think those are very open questions. So if you train your model, if you train your hydrologic model in the current period using the real climate data, and then when you forecast, you use, or you project into the future using a climate forcing, those two are characteristically different. Like the two are coming from totally different background distribution. Because if you run the climate model now, for the current decade, it's not going to give you the current climatology. So I think this question is actually, sounds simple, but actually has many turns. If we really want to do this, I think you have to almost go back in time and find a climate projection that was generated a long time ago, given the current, the initialization or whatever you have, to train that forecast in hydrology, in the forecast hydrologic network. Does that?
Can I jump? So when you're dealing with models trained on, say current conditions, and you're worried about them projecting the future conditions, basically what you're doing when you're training any model is you're essentially learning a bunch of points and a nice function that interpolates in between them. And that function, with some exceptions, is only good in the region of the data where you've trained it. If you get too far away, it extrapolates and it starts to become a big mess. So you can reduce that problem by training your model on data from a wide range of conditions, essentially simulated conditions that aren't real, that explore the nearby space in each of the variables. So it's sort of like a fake simulation of different conditions that don't exist right now. And the more you do that, the further you can push those boundaries until your simulation becomes basically illegitimate or out of bounds or extrapolating. And then another piece that is missing most of the time that I think needs to be there is you need a classifier or some other detector that's aware of the region in which you've trained your model and knows if you're inside or outside the region. So you either need an error bound associated with your function, and that grows when you go outside the value, or you need a classification boundary that tells you if you're inside or outside your training region. And when you go outside, your answers are not legitimate anymore, and you'll have to fine tune and retrain. But yeah, so you can mitigate that, but eventually you need to detect it.
So we actually looked at, we look at this multi-year trend, as we showed earlier in our talk, and the conclusion we took is actually LSTM was even better than the process-based models in terms of capturing the trend. And we can actually find the best model of all the models to compare it against. So sometimes, for example, if your climate here, I'm living in Pennsylvania, so if my climate in Pennsylvania has warmed beyond what we have seen in the past, then we probably become more like Virginia or Alabama, right? So somewhere in your domain, on the Earth, there is a more extreme guy than you, unless you are living right on the boundary, right? So you have some guy, because we are all enclosed in a wide variety of climates. So somewhere along the Earth, you have somebody that is more extreme than you. So I'm actually, due to my experience with the recent modeling, I'm actually less worried about that extreme part than about the climate model being characteristically different from your actual forcing, what you use to train your LSTM model. It's like, you know, you train it with real data, then you test it with climate data, but the two are so different. And I'm not sure how, there must be a very careful examination of this topic, which, you know, we're trying to get in, we're trying to do some, you know, examination of that.
All right, with that, I'd like to thank the panel again for speaking today and for answering all of these questions. So thank you.